Thank you. It's my pleasure to be here. I can think back a long time ago, and I'm sure, my life, maybe it was a moment that changed things, but the international sail training and changing lives, as I remember as a 7-year-old being in Boston when ships came to visit, and my parents were adamant that they were going to take us. And it really, back in those days, it was our opportunity to really see international exchange. Today, the society's more global, but back then, no. So it was a wonderful experience. I think it left an impact on me. This is a living document that I'm going to go through, basically, meaning that I want this to be a resource for people to use in the future. I'm going to go through a bit of meteorology describing severe weather, both thunderstorms and severe tropical and non-tropical storms, frontal cyclones. And there are links that are embedded within this document, such as here. And they point to either training material, sources of active information, operational information, a variety of different things. But again, this is intended basically for you to use well beyond just listening to me go on today. So let's go ahead and start. Just a brief outline, we are going to take a little look at Sandy from a meteorological perspective, but I have to set the stage first to describe the difference between extratropical or frontal cyclones and tropical cyclones. A little bit of a touch on European weather, where your sources are. There's just a few that I listed. I think you in operating here, you should know pretty much what's available to you. You have terrific weather services and resources, and you contribute globally to improvements in weather prediction. And we do collaborate. I know my colleagues in both the Met Office and throughout the European satellite community, and we exchange information all the time. I want to talk about thunderstorm basics. For those of us that were in the stability session listening to the microbursts, I am going to go through some of that information. And I have a couple of discussion points at the end. And I'm hoping if I do things right and Antonio keeps me on time, then we'll have time for questions and answers at the end. So let's go ahead and start. So this is a typical frontal cyclone. This is over the North Pacific. This is a fairly mature cyclone in its strongest state. It is not tropical in nature, but it is, as we've learned over the last 20 years, that the mature form of a frontal cyclone, inner core, this portion right in here, is actually quite similar to a tropical cyclone. And that'll play when I talk about Sandy for a little bit. And it does harbor extreme conditions, extreme wind conditions, and we'll see that in a little bit. Frontal cyclone, in that fronts are the difference between areas of temperature difference, and frontal cyclones tend to be very asymmetric when it comes to where the temperature contrast is. This is what we call now the bent back occlusion, and you can see that it spirals in, actually in this way, in towards the center, that extends out to an extension of the warm front. So there's cooler air here, warmer air here. This is the cold front, where winds shift from south to typically southwest or west. There's actually a secondary cold front right here, and you can tell that by this line of showers and then this area of open-celled cumulus clouds. Strongest conditions, strongest temperature contrast is actually right in this area, right here. Strongest winds are right in that area, right in there, and they could be as strong as hurricane force. This is a relatively weak temperature contrast. You have easterly flow here, northerly flow here, and this is in essence like a secondary warm front. All of the fronts are focus areas for wind, so that when you see a diagram like this, you should be thinking about wind, and that's where the wind shifts. It's also where the wind is strong, is right along the frontal boundaries. Okay. We live in an age where satellites have become more and more important. Right now, there are two operational satellites that we use that have instruments on them called scatterometers. And what a scatterometer is either a 2 or a 5 centimeter radar that scans the ocean surface. And by scanning the ocean surface, it actually is able to estimate the wind speed and the direction over a broad area. And I'll show you some examples of that. On the European side, we're very fortunate. We have METOP A, which was launched in 2006, is still operational. The instrument is called ASCAT for Advanced Scatterometer. And METOP-B was just launched in September of this year and is about to come online in the next month or so. And the two satellites are close to each other in orbit, and they will complement each other. We also rely on the Indian Space Research Organization, or ISRO. They have an OceanSat-2 satellite, and on board is a different type of scatteroma than ASCAT, but does in essence the same thing, except for it's a spinning mechanism. And that was launched in 2009, and the Indian Space Agency has been very, very welcoming to learn how to improve the data that they've developed with their instrument. They also are very aggressive in that they are the future of, along with the Europeans, of ocean wind detection from space. There's actually a fourth, but it is closed access, as China actually has a series in line of scatterometers. But so far they have not. They have an agreement with the Europeans to share internally, but they do not have an agreement to open it up. Anyway, so I'm going to show you some ocean winds over some storms. And there are links there to them. So here's a Pacific storm again. This is a different one. You can see California off to the east here. And similar type of structure to the one that we saw before. They're not the same storm. And this is what a scatterometer gives us. This is the wind field associated with the storm from two different passes from the same instrument. This is actually an instrument that was launched by NASA that stopped spinning back in 2009. This is QuickScat. Has a wide swath of 1,800 kilometers. And the color scale up here is wind speed. So the yellows are gale force. The oranges are strong gale. The browns to brownish red are storm force. And the reds are hurricane force. So again, I showed you the fronts. And if you map the wind field, especially in the area back here, this is the bent back front here. I was telling you about this sort of secondary warm front. You can see that that's a focus for wind with strong gales here to storm force, and then here is hurricane force down in here. Very large cyclone when you reference it to California. Okay, so this is one diagram that you might want to make a copy of at some point, is just to give you an idea. It's the evolution of the life cycle of a frontal cyclone. And the phase that I was showing you, the mature phase, or what we call, and even the Norwegians, who basically started the frontal theory, call it a warm seclusion. The center of the cyclone basically develops a warm, low-level warm core, and even though it's embedded in a cold air mass. And that warm core is similar to the structure, can be, to a tropical cyclone, to a hurricane. It's shallower, it's asymmetric, but at times it has the same structure. And it plays into, when I talk a little bit about Sandy. But you get an idea of the evolution of the wind field from the open wave here to just maybe some minimal gales to frontal fracture as the wave amplifies, and we do call it a wave, and continues to amplify as the cold front sort of slides underneath the warm front, and this bent back develops and starts to wrap around. And in this mature phase, this is the area down in here. In the westerly to northwesterly to northerly flow is where we often see the extreme conditions. Of course, there's different variants of this as they evolve, but they can happen at any time of year. North Atlantic, North Pacific, Southern Ocean, almost doesn't matter down there. It's always active. But this is one diagram you probably should keep in your head. So let me go ahead and talk a little bit about resources. This is a warm seclusion going across Scotland, and this is a colored image from European Meteosat second generation, or MSG. This is an air mass product where the colors actually, you see cloud, but you also get an idea of the depiction of the characteristic of the air mass. The browns in here tend to be dry. There's a great training material that if you look at one of the sites that I pointed to in the first slide, it talks about this type of data, but it's freely accessible on the internet. And I'll show you another image of this. But anyway, this is just kind of an advancement of an extension of just looking at cloud pictures, and we get an idea of the three-dimensional structure of the atmosphere. So it's a tool that we have, and this was a fairly significant windstorm that went across both Ireland and Scotland and into Norway. So tropical cyclones are different. They're non-frontal. Basically, they're born in the tropics where there's little temperature contrast. They go through a variety of different phases. In the Atlantic, they typically start as a wave or an impulse of thunderstorms over Africa. Some you can even trace back into the Indian Ocean, is the development of the cluster of thunderstorms. And in essence, they're an organized set of thunderstorms, and to a point where they can become very highly organized. So this is a wave that has come off of Africa, is not yet strong enough or does not have a circulation strong enough to delineate itself as a disturbance or a depression. Tropical storm Earl right here looks like it's ingested some dry air, but this is the next phase, tropical storm, meaning the winds of 34 knots or greater associated with the storm. And the ultimate state, and we have various categories of this is Danielle as a hurricane. There's an eye right here. The eye basically is sinking air coming down to the surface from aloft to basically you have convergence in an eye wall surrounding this column of sinking air that then comes and then is drawn back up into the vortex. So tropical cyclones can be as strong, the strongest of the typhoons in the West Pacific, but here in on the Atlantic Basin, they can be as strong as 140, 150 knots, a Category 5 on the Saffir-Simpson scale. But they're non-frontal. There's no, basically, it's a warm air mass until they start to interact with the mid-latitudes and move farther north. So a scatterometer view, this is a typhoon in the West Pacific, and this is from the Indian satellite, gives you an idea of the symmetry. Gale force winds, again, are yellow, strong gale, the orange. The scatterometer itself, because of the heavy rain in this area with an eye and the eye wall, has trouble detecting the wind speeds because they don't happen on the scale that the instrument samples. So you get a little bit of a false sense of security that it's not that strong in here, but in reality it is. It's masked by rain and by the resolution. But you get an idea of the symmetry as opposed to what I showed you with the extratropical frontal cyclone. So let's talk a little bit. The reason why I wanted to talk about Sandy, and I realize it's a sensitive subject, and I appreciate that because of the loss of bounty. I just really wanted to deal with the meteorological aspects because it's a very interesting, was a challenge to forecast for. I was one that was involved. I specifically was tasked with storm surge. We kind of had an all hands on deck within the Weather Service for this event, and we put all our resources imaginable towards it because we realized the threat, which ended up coming true. But this is from Thursday. Landfall was on Monday afternoon, Monday evening, and this is a 5-day forecast of the projected track. And just as a clarification, and it says at the top, this cone, we call this the cone of uncertainty. It is not a wind field cone. It is a cone to delineate basically the average forecast error over time over the last 10 years. So as this widens, it basically equals about 25 nautical miles every 12 hours of forecast time. So over 5 days, you can do the math as to how wide this cone actually gets, and it's reflected up in there. It's not the wind field. It is basically the cone of uncertainty. There are separate graphics on this site at the National Hurricane Center that you can go back and look at the graphics that go along with the wind field probabilities that go over time. Actually quite impressive because they're very, very large. So to set the stage for Sandy, this is the 500 millibar or 500 hectopascal height contours. You're looking at a constant pressure surface from a series of analyses from our numerical models. And there were several players along with Sandy. B is Sandy right down in here. This starts on the 24th. The 25th, I guess, is when I started it. The 24th. We're going to look at a loop. The big player it was this area of high pressure over the North Atlantic to the east of Greenland. It's going to migrate to the southwest over to Newfoundland over time. And this is a block. So whenever we have a blocking pattern, you have the potential for extreme things to happen. And basically, there's another block out here in the Pacific where you have a high heights over low heights. So you have basically high pressure over low pressure, and the flow upstream splits. And that's exactly what happens here, where you have a split going both ways. Another player is this trough here in the middle part of the United States, and there's a kind of an impulse right in here that plays into this trough as it moves inland, and all of this amplifies in here to lift Sandy first north, northeast, and then back to the northwest. So let's go ahead and see the loop. I just let it run a couple times. You can focus here first to watch how, and these are every 6 hours, how that block actually migrates down to the southwest and then becomes established. It will start over again. You get to see how that moves, how the trough amplifies right in here. Here's that impulse that's feeding in. It basically grabs Sandy and slings Sandy back into the northwest, into the southern New Jersey coast. And I'll let it go one more time. Complex situation, but actually was moderately well forecast. All things considered, of course, weather is sensible weather is what you experience is what's important. But on the larger scale, it was handled fairly well. Okay, so this is, my office does analyses every 6 hours. We're a 24-hour operation. And these are radio fax charts that are distributed via a variety of different sources and also available on the web. And this just gives you an idea of the track, the human analyst working forecast desk. And this is the analysis in time by a variety of different forecasters. We put our names on our charts so that people can identify sort of who we are. And actually, there's it's kind of a pride thing. Our forecasters really do like to sign their product because they feel responsible. That when you're at sea, you're actually under our care over the Western Atlantic and over the North Pacific. So that is kind of an extreme situation when you see how the isobars, the lines of equal pressure, consolidate and get larger and larger at this time. What a large circulation it was as it moved inland and impacted a very, very large area. But offshore, the conditions were just horrendous, especially off of New York right before landfall. So this is a 4-day composite track of a combination. This is the type of things that we tend to do now. This is an ensemble of models. It's 110 different global models. And what you're looking at is the probability of storm track composited over 4 days. And this was done the 12 UTC on the 25th of October. This was on Thursday before a Monday landfall, and gave you a pretty good idea as to where things were going to happen. So kind of give you an idea of the state of the art of where the science is. Ironically, we had an event a week later that ended up being a snow event, a nor'easter, and we struggled. Here we did fairly well with this event, and we really struggled with track, intensity, and then the snow. So we got a reminder within a week of, okay, you can rest on your laurels for about 1 hour, and that's it. You just keep on going. But I just wanted to give you that's kind of the product that we're doing. So back to Sandy, just to give you an idea of the scale. This is ASCAT, again, a European scatterometer, a METOP A. And Sandy, obviously, is right there. This is on the 26th of October. And gale force winds extending out this far. If you use Florida as a measure, you can get an idea as to how large the wind field is. And these are up to storm force in the brown. So you kind of see that it doesn't quite look like the nice symmetric tropical cyclone that I showed you from the Western Pacific, the typhoon, that it had sort of a hybrid behavior pretty much through its life once it had cleared the Bahamas and started to move northward. And you can see other things. This is fantastic data, and there are links embedded in here where you can go and actually see this for this region or wherever. The Mediterranean is another place where ASCAT really does very, very well, along with out over the open ocean. So this is the last pass of ASCAT, 1419Z on the 29th, with landfall being about 0Z on the 30th. And it gives you an idea of the asymmetry. The length of gale force winds from here, or the diameter, was almost 800 nautical miles at landfall. These are strong gale, the oranges, and this is one of our worries, was this area of storm force winds swinging in over southern New England and Long Island, which indeed it did, and had very destructive gusts. The strongest winds were similar to the extratropical, the frontal cyclone that I showed you, with an area of hurricane-force winds in the westerly flow underneath the cyclone to the south. So there was a very strong front, and in fact, where I live in the Chesapeake, we were in, about 4 or 5 degrees C. Up here in Long Island, they were at about 15 to 18 degrees C. So they were in the warm air while we were actually in the cold air. So it had very strong frontal characteristics with it. So kind of a different sort of beast. And my point being is that the frontal cyclones in the mature phase, the inner core, and the inner core, or the tropical cyclone, are actually quite similar. They're actually very, very close cousins. And in this case, this is about the closest that I've seen that the conditions warrant, the type of warnings, whether it's extratropical or tropical cyclone. Okay, and that's just a blow-up of the same. So weather services are divided up around the globe, a variety of nations providing the necessary information broadcast via GMDSS. And for the Baltic area here, or sub-area, the distribution office is the Met Office, but the actual office that does the prediction is the Dutch Meteorological Institute, DMI. And this is a link to the Baltic Sea sub-area that is on both the UK Met Office page and the DMI page, and broadcast a variety of different ways, from voice to Navtex. That's, and my office does this area, Med Area 12, Med Area 4, and my colleagues at the National Hurricane Center actually do this portion off of Peru at Med Area 16. And these are done by 3 different offices: the Honolulu Forecast Office, my own office in Washington, D.C., and the National Hurricane Center Tropical Analysis and Forecast Branch. And we do coordinate with our bordering partners when circumstances warrant. Okay, so you do have terrific resources here in Europe. And this is a Meteosat second generation, or MSG, red, green, blue air mass product. And basically the greens are really, really moist, so that's tropical moisture streaming northward. The browns to reds, like back in here, are and the purples are very, very dry. So you get an idea not only of the cloud shapes, but also the character of the air mass that's involved. There's a link down at the bottom. This is freely available on the web and updates every 15 minutes. Quite a terrific resource. You also have, there's 3 links here. 2 of them are U.S. One of them is Royal Dutch Meteorological Institute in De Bilt, Netherlands. This is ASCAT data, high resolution, what they call a coastal product, which they have basically worked to get the radar signal and the information, wind retrievals, as close to the coast as possible. Again, the same color scale, and this is from one day last week of the Baltic, and you get to see the coverage. You get 2 passes per day from the scatterometers. They're in a polar orbit, so you get a late morning pass, and then a late evening, almost to midnight pass. In fact, this is at the timeline right here is 9:59Z, so it gives you an idea as to what time the satellite, about that time every day, is when it would pass over, and then again at the 12 hours later. But you do get an idea as to the details of the wind field. It's great in the Mediterranean. I mean, the Mediterranean is a very complex place, and it's great to see the coastal jets and a variety of different features. Okay, so let me just talk a little bit for the rest of the talk, basically, about thunderstorms. And this is basically, we've had 2 incidents in the last several years, Bounty being the most recent, but certainly the incident off of Brazil that Bill Curry was talking about has been a focus in the U.S. anyway, and Canada, on are there things that we need to know more about thunderstorms in the traditional sailing community, in the tall ships community, in order to try and prevent incidents such as what Bill was talking about. So thunderstorm, basically, one thing is it has to have lightning. Okay, you can read the definitions. Cumulonimbus cloud basically means that it's a raining cumulus cloud. Has to have lightning and thunder. Really, the key is lightning. It can be accompanied with heavy rain, wind, hail, a variety of different things. It's due to instability. The atmosphere wants to overturn. Typically, you have warm air down low, warm moist air, cold air aloft. That's unstable. They want to overturn, and the way the atmosphere overturns, it doesn't do it all at once. It would be nice if it did, because then it would be stable. It likes to be stable. But instead, it tends to overturn in discrete areas, and that's where we have cloud formation, vertical motion, and all. So it's just a natural process, and unfortunately, with it comes wind, rain, reduced visibility, a variety of different things. And they happen on varying different scales, and that's what I'm going to kind of go through. So where do they happen? This is a 500 millibar height field, a global infrared composite from 4 different satellites, and I also have global lightning data that cuts off. I should quantify. It's not that there aren't thunderstorms in the Southern Ocean. It's just that our data feed stops at 25 degrees south. But where you see troughs at 500 millibars, out in advance of that, you see these channels of cloud. There's one right here, migrating northward. Those are fronts. Fronts are back here somewhere. And in advance of the fronts is where you have the moisture migration north. That's where the areas of instability occur. It's where the moisture is. It is where you end up with the thunderstorm formation. These are 4 hours worth of lightning data at a given time. Other areas, I mentioned cold air over warm air. This is an upper low right here, so there's a cluster of thunderstorms, and it's shown by the lightning. There's another upper low right here. And there's one right off of the Moroccan coast, just north of the Canaries, right here. You can tell by the circulation in the 500 millibar field. You do see lightning in the tropics. You can certainly see it over northwest Brazil. But lightning production is dependent upon ice processes in clouds. If you don't have ice, you don't have the charge separation, so you do not get lightning. So you may have cumulonimbus. You have cumulonimbus clouds, but they don't necessarily produce lightning. But you do see in the intertropical convergence zone some lightning strikes, but not as frequent as you see, say, in the 4-hour composite up in the westerlies, where the stability tends to be more, and you have colder air aloft. Okay, so just to sort of drive that point home, this is a parameter composite of something called total atmospheric moisture. So the reds and the greens are extreme tropical moisture. And you can see the pinks are lightning. You can see that basically those channels or rivers, they call them atmospheric rivers, of tropical moisture flowing northward in advance of fronts, that's where you end up having the thunderstorm and convection. You'll be able to feel that in this case it's actually separated, but you can actually see the moisture in here, that is the channel is right in there as to where the moistures come from, and same thing here from the deep tropical pool of moisture. So no coincidence that the thunderstorms happen there. Okay, let me go ahead to, this is a day back July of 2009. I actually want to go to the zoom of this, and you get to see, this is, again, 4 hours worth of lightning data. So you have a cluster here that's in a line, and it's actually moving in this direction. These are actually the granddaddies. These are actually supercell thunderstorms right here. Okay? Here's a line of storms up in here, a different characteristic, and even another line back in here of a different characteristic by the lightning trace. Not a lot of lightning with this prefrontal line. There's some up here, and in fact, what you could see, these cusp shapes, those are outflow boundaries. Those are the boundaries, wind that has descended down in the storm and pushed out, they push out away from the storm, and they're actually where new storms will form, especially where there are emergers from the boundaries, like, say, right in here, the boundary here, and here, and same thing in here. There's an outflow boundary right there, and there's one there, and that's where new storms would tend to develop. You can see that right here. in this cluster where the storm is developed. This is the leading edge of the boundary in visible imagery. So different places, different characteristics of the convection. So in the tropics, this is an easterly wave that's just coming through the Caribbean. And because of the ice processes are somewhat limited, there is some lightning, but there isn't an awful lot. But there's still significant rains. These tend to be a little bit more benign, squally, but not necessarily the strong dynamic thunderstorms that you have a little bit farther north. They're still to be respected. You could still have strong downdrafts with them, but they don't have the signature of the lightning that others do. Farther deeper into the tropics, the thunderstorms tend to be more upright, and they tend to be more single to multi-cell thunderstorms, and less of the dynamic, extreme sort of dynamic thunderstorms that we see farther north in the first image. So 4 different classifications: single cell, multi-cell cluster, multi-cell line, and supercell storms. I'm going to give examples of each of these. And this being the simplest case, this is basically an updraft, precipitation forms, and then a downdraft, and it does its life cycle maybe on the order of minutes. These tend to be more organized to the highly organized supercell. And the difference between the single cell and the multicell and supercell is the increasing shear with height, basically of changing wind speed, direction, and shear with height. And what that does is it allows the storms to have a separate updraft and downdraft. The more the shear, the more separate updraft and downdraft, the stronger the storm, the more long-lived that it will be. Okay? So really, the difference is, in part, it's the stability, or the lack of stability, as compared to the single-cell storm. But also, the driving force is the shear, in that you're able to separate the updraft and downdraft. Okay. So we call these single-cell or pop-up storms, pop-up, air mass, up and down. They're buoyancy-driven. They can have, and this is awful to go through. I've given this briefing several times, and I hate to say, but any one of these can produce a downburst of significance. And I'm sorry to say that. It would be nice to say that you have pop-up storms. It wouldn't be that threatening. If you're in the wrong place and you get a downburst, it's a downburst. They can occur anywhere, and they're generally disorganized. The downburst can occur anywhere in the sort of generally disorganized storm, and they're very, very difficult to predict themselves. The conditions overall, there's a chance of thunderstorms, but actually trying to predict the character of them is difficult. So to illustrate aboard your vessel, it's always good to keep an eye on the sky, to look at things, to watch the character of clouds as they change. This is a growing cumulus cloud, and has a very hard edge on the north side. It's not evaporating or fluffy. It's still punching up. You'll see that it's still pushing upward and is still growing. This has become very fibrous. This is ice cloud up in here. This storm has done its deal. It's done. It's dropped its precipitation, and basically you have debris that's left over, cloud debris. Meanwhile, you have new developments closer to you because you can see them. So always sort of changing, and again, the life cycle can be on the order of minutes to half an hour, but not much longer than that, and it makes it very difficult to forecast. Okay, here's a typical one at sea that, again, is fibrous at the top, and that's a good sign that it has gone through its process, is precipitating, and is coming to an end, and you can expect perhaps other storms to develop around that. Okay. Multi-cluster storm, multi-cell cluster is kind of a mix between the multi-cell line and just the air mass. It's longer lived than a single cell, and the difference is, because there's a little bit of shear, that it's able to separate the updraft and downdraft. Means it can live longer. Can also produce downbursts or microbursts, hail. High winds typically are near the updraft-downdraft interface, and I'll show a diagram of that. And they're a little bit more predictable than, at least in the short term, than just the pop-up storms. For one reason is they're a little bit more traceable in radar. And Anyway, so this is an example of sort of the life cycle from towering cumulus, the mature stage, to the dissipating stage over time. The key, again, being updraft, downdraft end up being separate, and it allows it to live a longer life and be a more efficient rain producer or hail producer. Okay. We're going to spend a bit of time on this. Multicell line storm is highly organized, longer lived than the multicell. Again, its instability is moderate and with moderate to strong shear. And again, the key is that the updraft and the downdraft tend to be separate. That allows it to be much longer lived than the air mass. These are more what you'd see in the westerlies, either in the more what you'd see in the westerlies in the diagrams that I showed you. Can be hailers. You can receive hail. Hail basically means, one thing, it's cold aloft. Another thing is that you have a strong updraft in order to produce and hold the ice aloft so that it can rime quickly as water, supercooled water, is migrated up into the storm. Then hail is able to grow and grow and grow until eventually, when it gets heavy enough, it can no longer support, the updraft can no longer support it, and the hail actually comes down. And sometimes it comes down in mass all at once and pushes air with it, and that's in part the process that, of a downburst. Let me go ahead to, this is a squall line or an organized line. This is the interface right in here. This is the downdraft. This is the updraft, and this is a shelf cloud that indicates that this is where the updraft starts to rise up, produces cloud that is sort of an appendage that's hanging down below, and is below the, there may be several shelves of these aloft, but this is the significant one. And right there is dust being kicked up. Sorry, I have to use a land example, but that's where most of the pictures that I can get are from. That right underneath that shelf is where the interface is, and that's where the gust is. That's where the gust front is. So that's where you're going to get hit by wind, is right underneath this shelf cloud, and I'll show you an example of that. This is what they call a rain foot coming down. So the rain is coming down in this area, and it's spreading out as indicated by basically the descending wind. So it's coming down, and then forced as it hits the ground, it's actually spreading out. So that's what a schematic, I just showed you a picture, but that's what the schematic is. And we're looking at this area of the storm here where there's a shelf cloud, updraft, downdraft, and the gust front is right at that interface, right in there. And it gives you an idea of the scale. I apologize, this is why I'll go to kilometers here, but up to 12, 13, maybe even 14 kilometers in height. So significant development. A planar view showing what, not all things, it's not necessarily a solid line, it may actually be a broken line of storms, and all depending on where you are, depends on what you experience, unfortunately. The lines themselves are made up of individual cells, and in this case, here's the cell here, here, and here. The cells are actually moving to the east. I was actually sailing under this, and I would describe, we were under this one, caught out on Chesapeake Bay, which says something, I'm a meteorologist, and we're caught out in thunderstorms. But it was what I would describe as a lightning barrage. I have never experienced lightning like that, that it just was constant. We never used, at night, we never had to use flashlights till actually the convection had moved quite a ways off because it was constant flashing. But we, at one point, got overrun by a cell. So the line itself is moving in that direction, but the cells are moving in this direction. And unfortunately, it's the cells that have the wind with them. So that you may be in a spot where you're thinking, well, it's this cell, this dark area that I see upstream of me, upwind of me, that is going to hit me, but in reality, it may be that one right there that's actually migrating to the east. So if I'm here, that one is going in that direction. This one may be the one that I have to worry about. And I'm going to show you a loop in a little bit that shows you basically how dynamic this is, a 24-hour loop over the Carolinas. Not of this one, but just so that you get an appreciation as to how rapidly things can change. That convection can explode, and we'll see an indication. And it can change its character very quickly. Okay. Green tinge means there's hail. Hail means there's a strong updraft. If there's a strong updraft, that means there's going to be a strong downdraft. It's not unusual. I've seen this quite a bit at my own home to see this greenish tinge in the clouds. It's a good sign that some bad things are about to happen, that it is a very severe thunderstorm. It's not unusual when you have this greenish tinge like this, or more of an opaque, like in this area or in here over a large area, that the storm itself will have an enormous amount of lightning with it. We have tornadic storms where I live occasionally, and typically we see a greenish tinge. Hail, they're usually pretty good hailers, and then also have a very strong interface between the updraft and the downdraft, so strong destructive winds. Okay, so the line storms, multi-cell lines basically, updraft and the downdraft. But what they can do is they can actually tap into the higher level winds in a what they call a rear inflow notch or rear inflow jet, where higher level winds actually feed back into the back of the storm, are advected into or migrated into the back of the storm and are able to come down to the surface. So, and I'll show a couple of examples of this. These end up being the stronger storms. They tend to be more in the westerlies, more in the transition from the tropics to the northern or southern tropics, extent of the tropics, depending on which hemisphere, and then more in the sort of the base of the westerly flow or embedded in the westerlies. So just to give you an idea, this is the line over time as to how the line evolves. This is the gust front here, delineated as a cold front. These are cells, individual cells with a rear inflow notch and jet, and this is where their strong conditions would be. And this is how it evolves over time. This is the northern hemisphere perspective. Time is here, so can be somewhat long-lived, out to 5 to 6 hours, and eventually they take on a comma shape with potential for severe weather in this area. So the migration is in this direction, west to east. We had one of these go through New York a couple of years ago that really did quite a bit of damage in the harbor as a relatively solid line. We had an event in the mid-Atlantic that it went across the Chesapeake of going from 0 to 60 knots in no time whatsoever, called something that was a solid line, not just like this, but all the way along. For several hundred miles back in June that took power out for some places up to a week and a half. It's called a derecho. It's a special kind of solid line of the thunderstorms, or bow echo. It's sort of the extreme. So again, to reiterate, that basically you have a rear inflow jet. You're not going to be able to see this, unfortunately. You see the cloud shapes that go along with it. But at mid-levels, and then descends down rapidly to spread along the surface. So it's these arrows right here that come down and spread along. And you typically have a very vertical, this is precipitation, so maybe hail or rain, but you typically have a vertical structure, and then this jet is able to come in to the rear and drive down to the surface and do destructive damage with the winds. And they happen over the water as frequently as they do over land. Okay, so I'm just going to a couple of high points. So this is basically bow echoes, long swaths of damaging surface winds. They can be either isolated convective systems or more like an organized squall line. An unstable environment in moderate to strong shear, and shear again being the difference in the wind speed and direction with height. They have a rear inflow notch, and you in the radar signal. In the weather radar, you'll see basically this notch behind the core of the bow, and I'll show you that in a second. And it signifies where the inflow is coming from, and then it points to where the destruction of winds are going to be. Again, it descends rapidly down to the surface. So here's two examples. Right in here, that's lower reflectivity. Here's the bow right there. So that's a rear inflow notch right there. And this destruction was occurring in this area. And similarly, in this case, another dry notch or lower reflectivity notch pointing forward, And again, in this area is where there was a bow and then also destructive winds. The sad thing is you can't see this with your radar, with your vessel radar. Your signal's going to be attenuated by the heavy rain. You'll see the leading edge of this, but you probably are not going to see, unless you have a 10-centimeter radar and you're on one of the Class A ships, you're basically going to see the leading edge of the thunderstorms, and you're not going to see the depth of the thunderstorms. Our weather radars that we have, the network we have over the United States, are the equivalent of 10-centimeter wavelength. So it allows us, and they're also, they're a parabolic dish and not the dish, say, that you have, so that we can focus the beam. It's got a half a degree width, so you really can see details inside of storms. Unfortunately, the marine radars, you focus this way. You're meant to see the surface. You're not focused the energy this way, so it actually scans like that. So you see basically the whole system. So anyway, supercell is the sort of the grandiose of all storms. It can be very long-lived. I'll show you an example of the Tuscaloosa tornado. They do happen over the ocean. I showed an example earlier. They're highly organized. They occur in very strong instability and shear. They have a long-lived separate updraft and downdraft. They actually split, where you can actually have two. Over time, what happens is that think of the shear as increasing with height. So you have sort of this rolling motion. If you can take areas of precipitation and then you take and twist that rolling motion, then you have one rotating this way and one rotating that way. Depending on the shear, depends on which one of those actually lives longer. So you actually can see, and I don't have an example of that these actually, they'll split into two storms. One will die, one will keep going. Left mover or right mover. It depends on the shear profile as to which one lives. The destructive winds are downbursts, again, near the updraft, downdraft interface. And I'll show you a picture where in the rear southwest storm flank. Some on the southeast flank. The example I'll show you has both. And they're relatively highly predictable. This is over the United States. It's a U.S. perspective because we focus on severe weather. We have so much of it. So that's an example of what one looks like in cloud. I showed you an example earlier. This is the overshooting top up here. So that's punching up into the stratosphere, whereas this ice cloud is capped. The part of the anvil is capped by the stratosphere. But there's enough momentum that it just keeps pushing up. There's so much vertical motion. This actually stormed. This was over eastern Maryland, moving offshore. There's another one to give you an idea that's actually from the space shuttle, looking down on a severe storm. And again, this is an overshooting top and an indication of severity of a storm. So in radar, you actually have a comma shape, and that's what you're seeing in here. So this is what we call a hook, and that's basically right in there is where there would be a tornado. And this here is a gust front, as is this down in here. So this is that southwest flank, and this is sort of the southeast flank of the gust front. And if hail would be up in this area, and I kind of consider this also to be the drop zone, that if, in essence, there's a tornado, that any of the debris that gets lifted is then fed into this area and then falls out up in this area. So it's not unusual to have hail and then also have debris coming down. I got to experience this one time at my own house, and my grass was pink because of insulation. We had a tornado that had passed south of us, and it had shredded homes, and there was insulation in the grass the next morning and little pieces of wallboard. A little sobering. Okay, that's the Tuscaloosa tornado, which lasted 8 hours, went across 4 states for 380 miles. The storm did, not necessarily. It dropped tornadoes on and off. Tuscaloosa being right here. It just narrowly missed the campus of the University of Alabama. But you see that hook shape all the way along. And there were other storms with this. They typically don't happen alone, but this was a monster tornado that went through. Do tornadoes happen at sea? I think we have evidence that, yes, they do. They're relatively rare, but they do happen at sea. They may be on the extreme waterspout scale is more of what I would think that they are. But I know I've seen examples like, say, in the Tasman Sea and a variety of other places where there have been pictures of tornadoes at sea. But more the line storm, the bow echo, is more of what you're going to experience, and that's enough of a problem as it is with the downbursts. So let's go ahead, and I'm going to go past this. So this is just a loop from a day in April of 2011 over the eastern Carolinas and moving offshore. It's 24 hours every 5 minutes, and I'll let this run a couple of different times. So you can kind of see a variety of different line systems that develop. Now, it disappears out here because our radar coverage stops, because we don't have radars at sea. But you can see a variety of different lines that form and are migrating to the northeast. Here's some cells that develop and then strengthen in here. And then right in here, you're going to see some pinks and purples. Those are supercells right along there. Those are tornadic, hailing storms, and then followed by a squall line afterwards. I'll let it go one more time so you can see. And then, of course, that moves offshore as a strong, solid line. Just let it go one more time so you can see. It's quick, fast evolution. It's explosive, especially the supercells here in eastern North Carolina, right ahead of this line, right in there. Those cells right there, those are supercell thunderstorms, followed by a line. So you would get hit by potentially downdraft from that and then turn around and get a squall line afterwards, which is not that unusual. So just very dynamic, and again, we see this type of behavior off the coast of the United States over the warm waters of the Gulf Stream relatively frequently with thunderstorm activity. Okay, so two different types of downbursts, basically. A macroburst, which is a larger scale, and a microburst. No, in the U.S., we do not use a wind speed definition with macroburst and microburst. This is the definition, basically, is on the matter of scale. Greater than 2.5 miles in diameter, or less than or equal to 2.5 miles in diameter for a microburst. And again, this is, I was in this also, and took this picture. Again, the appendage hanging down. You can see a little bit of rain coming down in this area. See, the wind is right with us at this point. And then we had wind and rain within a few seconds after that combined, blew about 35 knots, blew itself out after about 5 minutes, and was another nice day. But if you're not prepared for this, if you have everything up, you're not watching the sky, then you can have your hands full. We had everything down, flaked, and sail covers on, and people down below that would be in the way, and did all the things that we should have done. Fairly frequent occurrence on the Chesapeake where I sail. Okay, so again, downburst, basically evaporative cooling in the mid-levels with dry air coming in. This is the rear inflow notch. That air then comes down rapidly and spreads out along the surface. It can come down into specific areas like this. What I like about this picture is you have this core of descending wind, a high inclination angle as far as the surface goes. So coming down and then spreading out over time and actually rolling as it does. The focus in the U.S. and in other places on downbursts really changed in the mid-'80s after several aircraft accidents, in particular Dallas-Fort Worth Delta jet, L-1011, went down. And basically, the plane was in an area of strong vertical motion pushing it down, but then once you get on this side of things, you actually have a very strong tailwind. Well, you're in a stalling situation, and that's in part what the aviation danger is the planes can stall because the vertical motion is so strong and that the tailwind, what was a headwind to vertical to a tailwind, basically causes the plane to stall and hit the ground. So two different stages of a microburst. The contact stage, that's when the wind comes down to the surface, and then it spreads out over time, migrates horizontally, and actually can roll. And you can see that in, this is the post-contact stage, so this is the rain foot that I talked about earlier. So the shaft of descending winds is here, spreading along, picking up dust in here and dirt, and then actually rolling back upwards. So you can kind of see that tube that's rolling. Unfortunately, this is a dark picture, but this is a dry, there's two different types, a wet and a dry microburst. Since we're mariners, we're talking primarily wet microbursts. But fairly benign cumulus cloud. It does not look that impressive whatsoever. This is a dry microburst. This is the burst right there. So the wind has come down and is spreading along horizontally and kicking up dust in that area right there. So unfortunately, these happen typically in the American West, in the Great Plains and the High Plains, but they can happen over the ocean also, unfortunately. It's another wet microburst, and you can see the rain foot again and sort of the rain coming down in this area. So a cross-section, this is a radar cross-section through a storm that produced a microburst. The pink in here is hail. So all that, this is the upright core, and this is hail. And what happens is the updraft starts to weaken, or there's so much water loading and hail loading in here that the updraft basically collapses, is forced to go the other, basically to reverse and collapse downward. So when this descends, it descends rapidly, pushing air with it and taking air with it as it descends down, and that's what basically comes down and hits the ground, can go in either direction, in any direction, like in a vortex. So like that. And this is just about the contact stage of a microburst. So you get the rain shafts that are associated with it. This is actually an air mass storm, but all that is coming down. You don't see a lot of wind away from it because it's still just in the contact stage and spread out afterwards. You can see that the rain foot here is starting to form as it's spreading out. So let me go ahead and I'm going to step you through last couple of slides. This is the precipitation core. This is a radar, three-dimensional radar depiction of a real set of storms. There's an outflow boundary here. That's what's indicated there. There's a second outflow that's back here. So this is the outflow of the downdraft in here. So you want to watch in this area and then watch how this core descends over time. And actually it's still developing at this point. Then as developing, it actually punches up an overshooting top. So the stratosphere starts about here, but it's punched up into the stratosphere. And so here's the maximum of the core, and it starts to descend. And again, here's the outflow right here with the wind. So it's now the precipitation core is descending. There's a higher reflectivity, probably by hail, right in here. And this is the second outflow. You have the first one here that's weakening. This is the second one, and this would be the strong one right in here, where you would have the interface, the strong winds. Again, it continues to descend, and these are every 5 minutes, and then down. So in about 15 minutes, basically the storm, in essence, is collapsing, but has pushed out this outflow right here and produced a downburst or a microburst. And last one. So the evolution is similar to what I showed you before for a bow echo. It's actually quite similar for a downburst. You can this is the core of the downburst in here. And as it follows along, you get to see the idea of first the rear inflow is focused into this area and then into here and then sort of spreads out over time, and this weakens over time. So anyway, just to kind of give you an idea as the evolution as to how in time, how it works, and I showed you in the vertical. So with that, just some discussion points, and then I'll go one more slide beyond that. But all of us have, we're operating at sea in a variety of different capacities. One of the things I think that we can hand to those that are going to follow us is basically situational awareness. Looking at the sky, looking at the conditions around you all the time, keeping a log. Do the things that prudent mariners have done forever for specific reasons because it works. To a degree, it works. Realize that the atmosphere is extremely dynamic. It can be explosive. And that's why I was trying to show you the Sandy example, on a large scale, and then show you the thunderstorm examples as to how rapidly things can change. When Mother Nature does not like instability. When it has instability, it wants to turn over and wants to go back to a stable condition. Unfortunately, that process is what gives us weather and gives us severe weather. If there's a way, and we've learned this on the professional meteorological side, if there's a way to integrate information into one place, so you're not looking around to a variety of different places for information, eventually you will have information on your ECDIS for meteorological information will be fully integrated in. That's being worked out through the International Hydrographic Office. There are different ways, chart plotters and all, now that if you're in close to land and you can receive information, you can look at radar and that sort of thing. But that's sort of few and far between. But anything you can do to better integrate your situational awareness tools is a really good thing. One thing I don't have up here is basically training. Teach your students, teach your sailors, focus on the sky, to focus on the water changes. What do they mean? Ask questions. Make sure that that's part of your discussion, okay? Each day that you're operating, have an expectation. Just remember that expectation, you may have to adapt that with time. The evolution may be faster than anticipated. I've tried to focus on examples that are explosive for that reason, that things don't happen slowly. Sometimes they happen very, very quickly. A good sign in the morning, if you're near shore, is to look at if there's a mid-level cloud of what's called altocumulus castellanus. They're sort of puffy mid-level cloud, and they're typically an indication that you're going to have a day of thunderstorms, that you have thunderstorms later. Also, if you can see the cloud layers, see which way they're moving, because that gives you an indication as to whether or not you have shear. If they're moving in different directions, then you have a shear profile, and that may mean the character of the storm. Remember, the strength of the storms that I went through, each one, the stronger the shear, the more the separate updraft and downdraft, the more violent the storm can be. Okay. Know if you're in the westerlies or the tropics, because you typically will have more shear in the westerlies than the tropics. You can still have downbursts in the tropics, but they may be more violent in the westerlies, especially. And I don't mean by latitude, because there are times when we get the westerlies to drop down far enough south so they're actually in the tropics. It actually happened with Sandy. So know basically where you are atmospherically, not necessarily latitudinally. And you have a variety of tools on board. Use them. Okay, be weather aware, be weather sensitive and make it part of sort of your ritual to always be reevaluating as to what's going on. You can use your own radar, but again, remember that if you have strong storms, you're going to see the leading edge of the storms. You're not going to see the depth through the storms. So you won't get an idea of necessarily the severity of the storm or the duration. You may just see the leading edge, which may be enough right then and there. But you can track and do that. Play with your sea clutter and rain clutter to try and you need the radar anyway if you're going to be in restricted visibility, but to try and get a better idea as to the character of the storm. If you have multiple radars, you're really in good shape. So I'm going to end there. There are more slides that are attached. There are resources, links, and a variety of different things that are there. And I'd like to open it up for questions.